to this session called Let's Write a Toy Language from Scratch. We'll see how to get from 0, so text input, up until execution, and a few explorations on programming models. So this project started as a low-code data manipulation UI in TypeScript. The goal was to write little data accessors and mutators in this language called OVO, with a graphical node editor, and to write little API endpoints by composing these little programs. I stopped this TypeScript version and now work on it in Elixir. So here are two samples of OVO programs. You can see that the syntax is a bit Elixir-like, but not totally. On the left, there's a simple header that we can see here that bar is a function that takes one argument, captures the value of foo, and when executed, evaluates to 9. On the right, there's the basic recursive Fibonacci example, which shows that I don't have infix operators. At least I didn't at the start, except for assignment. I changed my mind later, but we'll get to that. So this evaluates to 8. We'll see what the bang is later too. So to get to execution, I followed 5 big steps. The first step was tokenizing my input to get from program text to a list of tokens by working characters recursively. Then I parsed that list of tokens into an abstract syntax tree that represents the program with parser combinators. Then I worked on a little printer that goes back to the text form of the program by working that tree. And I explored a few rewrites and transforms, like if you want to modify your program before running it, it's a good place to do it on the syntax tree with pattern matching. And finally, we can see how to evaluate that tree up until there's a single node left, which is the output value, with a tree walking interpreter. So, tokenizing. You're not forced to do that. Some people like to parse text directly, but I work in a more straightforward way with tokens. So it's a step where I let go of white space and formatting. And if you were to go to proper error handling, you would add metadata to tokens like the line number or character numbers to inform the user about errors. So my tokenizer is quite simple. It's only 2 recursive functions, walk and hack, with a lot of clauses for walk. I start in an undefined state, and some tokens trigger state changes, and we recurse through walk and hack until there are no characters left. Here, a character is what is defined by the output of string.graphemes. So when the state changes, I emit a token. So the thing to watch for is, are we inside some long token, like inside a string or a number, or do we have some short token, like this arrow, which emits directly? So in code, you can see that I have a lot of very simple clauses that call hack directly. Then I have some more complex ones with logic for inside a string or inside a number. But when the mutual recursion between walk and hack ends, we have successfully tokenized our input. Sorry for that. So the second step is parsing this list of tokens to answer a simple question. Does the token list form a valid program? So, because the tokenizer is not concerned with whether the input is valid or not. And by answering that question, we create a syntax tree that represents the program without syntax. So here we see that a call to foo without arguments is parsed to a root node that has as a children a single function call node with a single value of a symbol with the value foo. We don't have children nodes because we don't have arguments to this function call. The way that we parse the list of tokens is by combining very tiny parsers into larger parsers. So we can see that parsing in expression is a matter of successfully parsing any of a shake. We'll see what that is, a lambda, an assignment expression, an infix operator that I finally added, a condition, a call, an expression with parentheses, or a value. And we can see that a value is any of a number, a string, a symbol, a list, or a boolean. We can also see that I work with anonymous functions since we have this dot syntax, and we'll see why in a minute. So a successful parser emits AST nodes. So the AST is the abstract syntax tree that we saw earlier. We can see that if this parser for a multiple element list matches, we emit an AST node with a kind of list and child nodes as children. What I like with these parser combinators is that it reads like French or English if you want. So we can read that parsing a multiple element list is a matter of matching an open bracket, then multiple times maybe an expression followed by a comma, then a last expression since it's a multiple element list, then a closing bracket. If we match all of that, we emit, otherwise we fail, and the next parser in a list is called. Failing parsers, of course, could inform the user with position and nature of the errors if I added this metadata at the start. So if a parser is a function that goes from tokens to AST nodes, combinators are higher order functions on parsers that ultimately return parsers. So we can see the then combinator here that takes a first parser and a second parser. And this could be a with expression, but if the first parser succeeds and the second parser succeeds on the remaining input of the first, we emit the concatenated result of both parsers. So usually you would use Nimble parsec in production code, which works with macros. So the syntax is a bit lighter, it's compile time, so there's no runtime cost. Here I'm creating a lot of functions on the fly, but it's quite rewarding to implement parser combinators. I encourage you to try it. Here's the either parser combinator, also called choice, which is a Boolean OR between two parsers. And with that, we can see that we can parse larger expressions into larger trees, like this list with a primitive value of 1, a string, and a function that takes an argument, doesn't use it, and returns an integer. And this reads quite easily in the tree form. So now that we have a tree, we can print it back to text. I didn't make a proper printer, but it was still useful for the next steps because any printer gives you a standardized form of your input text. So maybe it adds line breaks at places that aren't exactly what you would do as a user, but at least it's always coherent. So you can use that in tests to debug your parser at the start and mutually debug your parser and your printer, since parsing input should be strictly equivalent to parsing back printed input. You would implement Elixir's inspect protocol, which is exactly made for that kind of use as a better way, but it's still useful. The way I print is by walking the full AC, and I have a function clause for every kind of node. So it's quite simple. Printing a list is an opening bracket, then mapping over the nodes with print node with a comma between them and a closing bracket. You can see I have clauses for every kind of node, but it's very short code. The fourth step I took is to think about program rewrites. So Elixir is very well suited for that with pattern matching. The idea is to recurse over the whole AC, just like I did in the printer, but instead of printing, you take that as an opportunity to match on specific patterns. Like here, I match on an infix node with a value of op, which is the operator, and left and right nodes, and I rewrite it to the built-in function calls that they were equivalent with, since I didn't have those infix operators at the start. So you just write the pattern visually that you want to match and write the shape that you want to get, and rewrite the child nodes too, so the whole AC can be rewritten. Maybe you think in a better way in nested structures than in text, and I think it's a neat way to modify your program. You can do that for more complex examples too. Here, it isn't very efficient to do that, but it's an illustration on matching on more complex inputs. We match on the ID to map some inputs, then filtering the results of this call to map. So map list is the output of map and the input of filter. And we can express that visually in our function clause, since name1 here is the same symbol as the first argument to filter, which match this specific condition. Then we just construct the equivalent HT of this big expression, and we have our rewritten code. So we can see it here, and by seeing this, we can, I think, appreciate the fact that we have a great macro system in Elixir, and we don't have to do that. But still it works, and by recursing over the whole tree, you can transform your programs that way. Okay. Before talking of evaluation, everything that we just saw has deeply practical uses. In addition of helping you think in trees, I encourage you to watch Riccardo Binetti's talk from CodeBeam Europe 23, which was titled Craft Your DSL with Nimble Parsec and Ecto. And he explains in a very interesting way why parsing things like that with combinators is useful. So, evaluation. Now that we have our full program tree that has been rewritten in some cases with my little transform passes before, we can match and recurse on the AC until we have a single value left. So some nodes like assignment update an environment with the value of this assignment, and some nodes just go to evaluate a level deeper. You can see how a condition is implemented too. So a condition node has exactly 3 children, a predicate, a first branch, and a second branch. We recurse into evaluate to get the value of the evaluated predicate. If it's true, we evaluate the first branch. If it's false, we evaluate the second branch. And we always return the environment and the resulting value of this evaluation. My environment and scopes are processes. In fact, they are agents. I wanted to juggle with PIDs. And speaking of that, you shouldn't use agents for that. There are lots of other solutions like ETS, but I want to play. There's a super cool talk by Brian Underwood, who's today's track host from Codebeam of last October 2, that was titled "You Might Not Need Processes," and I also encourage you to watch it. It was very interesting. So when we have function calls, we either call a built-in function or a function that the user defined in the language. This is quite crucial because if you choose well your built-ins, you can do more work in the language. If your built-ins are too sparse, you have to work by adding more built-ins to the language, so working in the host language. And in retrospect, I didn't choose my built-ins very well, so as you can see, I have quite a lot of them, and I could not implement filter, reduce, map, or that kind of things by just implementing list construction and deconstruction operators, just like you would do if you did a toy Lisp. Anyway, a built-in function pattern match on the evaluated args, so we can see that the built-in concat matches for 2 strings or 2 list nodes and re-emits the node that corresponds to the operation of concatenation. So this is how you reduce nodes to little values at the end. And this is how you get to evaluate a full program, like this mapping of a list with 3 elements, on which we add 5, then filter for inferior to 7, and we get a list with a single integer node of the value 6. So what do we have at this point? We have a thing called OVO that evaluates little programs. It would need a lot of fuzzing because every new program brings a bit of holes in the parser of our tokenizer. It would need error handling, but it works very well as a creative outlet. So it doesn't do anything special yet. So I have the steps to build a language, but it doesn't do anything interesting. And while thinking about what it could do, I think the beam with its actors, its state handling, concurrency, and distribution influenced my thinking. So I went to explore a stateful system. The first feature of the stateful system was the ability to shake functions. It means that when you prefix a function with a bang, internally it creates a stack of its results that you can't access directly, but that you can shake later to pop a value of the top of the stack. So when we call sAder, which is a shakeable function, the stack gets pushed with 11, then 17. Then when we call it back with 2 shakings of it, we pop 17 and 11, but we push 28 since it's the result. And when we call add with 28 and 28 that was on the stack is empty, and we get 55 as output. And of course, it's your responsibility to not shake an empty stack. Building on that, I started to think about program runners. So there's a registry of programs, and programs are registered as runners, which are a little description, the code, and the AST. And every runner has a stack of results too. And from OVO, you can call airshake with the hash of a runner to pop a result from the stack. So you can have interaction between multiple programs that you can compose. The hash of this multiplier program, for instance, is 1i9jp, which is the five first characters of the MD5 of the print of its AST. You can also have cheap program composition with run chain. where runchain ABC on some args is equivalent to calling A on the args, then B on the result of A, then C on the result of B. So it's kind of composition between programs. And I then went to experiment with LiveView, because I write quite a lot of tree editors for work, but usually in TypeScript. So I wanted to start with LiveView. So by walking the program AST graphically, by emitting HTML nodes and forms, we can have two-way editing of a program. We can see that like in a tree editor, you could add nodes. Of course, it's lacking features. You would need to be able to swap nodes, to change their type, to copy subtrees, and to paste them elsewhere. But it's a start of the idea of what I would like to do. And different node types are rendered by different input types, and the program text changes. And changing the program text changes the GUI on the right. So with this ability to graphically define runners, I went to build a little runner dashboard. So this is a live demo of an idiomatic OVO implementation of the bottle song, which is a famous little toy language example. So there's a joiner runner that joins strings. There's a register runner that just logs its argument, but in OVO that means filling a stack. And there's a filler runner who just calls the register 100 times with a value that decreases. So to run the bottle song, we just pre-fill the register with 100 results. Then the full program will pop this register to evaluate each bottle number. I could just recurse like in the filler in the full song, but that's not idiomatic OVO. We can see that this is built on invoke, which allows to call a runner from another runner. So if we run it, every runner gets its stack filled, and we have the whole song text here. So it's quite basic, but it's also quite neat. The next thing I thought is that programs didn't need to be on the same computer or node. So I started to experiment with multi-user program composition, and there's a fictional conversation between Alice and Bob. So Bob needs a hash function, and Alice tells him, okay, just invoke sj2py at my node with a string as the first argument. So if we go on Bob's side, we can see that he made two runners. Bob's interface is in pink, so we recognize him. So if he hashes the quick brown fox on Alice node, he gets a hash. And on Alice node, we can see that the stack of her runner got filled with Bob's hash. So this is not a cryptographic hash function. It's more like a hash map, a key hash function. It's called the Jenkins hash. It was simpler than MD5 that would take a lot of pages, and I'm not even talking of SHA or Bcrypt. So with his hash, Bob is confident, and he will now proceed to hash his password with this second runner that has a secret argument. So he runs it and gets a hash. But on Alice's side, we can see that Alice swapped her runner sj2py because she found another OVO program with a magic value here that hashes to the same identifier. And this allowed her to own Bob and log his password. So that's it for the demo. There's still one thing I would like to build on that, and it's more concurrent and time-based. It would be the ability to link runners inside a kind of graph, where runners depend on each other's inputs and outputs. But computation would advance of a fixed number of reductions at each bit. So maybe a program takes 3 bits to run, maybe a program needs 10 bits to run. So runners should have to wait for some others to complete. Maybe some queues of inputs would fill up. Maybe some queues would be consumed too fast. And I think of it as a kind of crossover between Patapon, which was a very nice rhythmic game on PSP in 2008, and the Erlang Observer, which has a kind of those graphs of processes and reduction counts. So that's it for today. The code is on GitHub. It's not very clean. It's an experimental project, but anyway, feel free to fork it, and feel free to drop me a message if you want to chat about programming models or some kind of things. Thank you for your attention.
Okay, thank you very much. So I just wanted to check first, is there anybody has any questions? Maybe post in the QA. Oh, we do have a question. Yeah, so Arpan asks, maybe you can see. I'll just read it out just for the recording. Given a problem of parsing, when do I use LEX, YEEC versus nimble parsec versus some self-implementation?
Okay, I don't have experience with YEEC, but if I recall correctly, you have to feed it a BNF grammar.
And I was going to ask just a quick question. Have you ever played the game TIS 100? It's this computing parallel processing game. It's fun. Maybe check it out. Your visual interface very much reminded me of what the game looks like. So.